Both of these are Godot. This is the built-in glow, the one everybody turns on in world environment. And this is the same scene with about 40 lines of shader on top. Look at the warm bleed around the highlights and that blue horizontal streak of the tube light. This is not a texture and it's not the built-in glow, because the built-in glow literally cannot do it. In the next few minutes, I will show you exactly how to build it. Let's be fair to the built-in glow first, because it's genuinely good. In world environment, you flip on glow, set a threshold, and Godot blooms your bright pixels for basically free. For a lot of games, stop there. It's the right call. But it has 3 ceilings. 1, it's white and neutral by design. Real film doesn't glow white. It glows warm and slightly orange because the red sensitive layer of the film bleeds the most. That warm bleed is called elation, and it's half of why footage reads as cinematic. 2, the built-in glow spreads every channel the same amount, so you never get that subtle color fringing on the edge of the halo. And 3, the big one, it can only ever bloom outward in a circle. It cannot do a directional streak, so no anamorphic look ever. Here's the entire architecture before we write anything, because it's simpler than it looks. A post-process effect in 2D is just a full screen rectangle with a shader that reads the screen behind it. In Godot, that's a color rect stretched to fill on a canvas layer with a canvas item shader that samples the screen texture. We stack a few of them. Each one reads the result of the one before it, does its thing, and so on. Tree order is draw order, so the chain just reads top to bottom in the scene. Ours is bloom first, then the anamorphic streak, then a couple of finishing passes we won't cover today. And that's it. 2 shaders do all the heavy lifting, and they share the same core trick, which we'll build once and reuse. Before bloom, we build the 2 pieces every one of these effects reuses. It's in util.gd shader inc, and it's tiny. First, Luma, the perceived brightness of a pixel, the standard Rec 709 weights. Green counts most, blue least, and it matches how your eyes work. Second, the star of the whole video, bright pass. Bloom shouldn't smear your whole image, only the highlights, so bright pass is a soft threshold. Below the threshold, it returns 0. This pixel doesn't glow. Above it, it ramps smoothly up to 1 across a little knee. The knee is why the transition is in an ugly hard edge. That's it, a smooth step on Luma. That one function is what turns a blur into a bloom. Now, the trick that makes it cheap. A white, soft glow normally means a big expensive blur, sampling dozens of neighbors, so we cheat. When we declare the screen texture, we add filter linear mip map. That tells Godot to build mip maps of the screen, downscaled copies, and a downscaled copy of an image is a blurred copy of it, for free. So instead of blurring by hand, we call texture load and ask for a higher mip level. 1.5, 3, whatever. Higher level, wider, softer blur. One texture read gives us a blur that would have cost a lot more. Every effect today leans on this. Bloom, the streak, even lens dirt. Learn this one line and you can invent your own screen effects all afternoon. Now, bloom.gd shader. And it's short. The plan? Read the highlights, blur them wide with our mip map trick, tint them warm, and then add them back over the original. Highlights first. We sample the screen at a blurred mip level, run it through bright pass, and we've got just the bright regions pre-softened. Because we read from a mip, the glow already spreads past the bright pixels themselves. That's the whole illusion. To make it round and smooth, we sample it in 2 rings around each pixel, 8 taps each, 1 ring tight, 1 ring wider, and read from an even blurrier mip. It's cheap, and it reads as a soft circular halo. Then, the 2 lines that make it filmic instead of gamey. 1, the tint. We multiply the halo by a warm color, a soft orange, before adding it. That's the halation. Instantly your highlights stop looking like a white video game glow and look like light through a camera instead. 2, chromatic aberration inside the halo. When we sample the glow, we push the red channel a little further out than the green and the blue a little less. So the edge of every glow fringes, red on the outside, cooler on the inside. It's subtle and it's exactly what real lenses do. The last line, final color equals original plus halo times tint times intensity. And it's additive, so it only ever brightens. Drop this color rect over your game and your lights bloom warm with a fringed edge the built-in glow can't do. This is the final result. The horizontal blue streak that fires off every bright point, the signature sci-fi cinema lens. Real anamorphic lenses squeeze the image, and one side effect is that flares stretch horizontally and tend to go blue. We're going to fake exactly that, and it's even shorter than the bloom was. Placement matters, so notice this. The streak shader runs after the bloom. It reads the already bloomed screen. That means the bright sources it works from are already broad and soft, so the streak has something juicy to smear. The effect itself. For the current pixel, we walk left and right along the horizontal axis only, sampling the highlights at each step, using the same bright path and the same mip-map blur from before. We weight the samples in a triangle, strongest at the center, fading with distance, so the streak tapers instead of ending in a hard line. Sum them, tint the whole thing cool blue, scale it, add it on. That's the streak. That's the entire thing. 2 full screen rects, 1 shared bright path, 1 mip-map blur trick. That's the gap between I turned on glow and wait, how did you render this? If you want, I can do the finishing passes next. The lens dirt reveal and the film grain that sit at the end of the same chain. Or go deep on tuning this for a totally different non-sci-fi mood. Tell me which in the comments. And thank you for watching.